Yes. Good morning, participants. I am Dr. R. Koteshwaran from Department of Instrumentation Control Engineering of St. Joseph College of Engineering. And we, from this department, we are organizing the seminar titled Reinforcement Learning. The speaker is Mr. S.M. Jayasurya. About our college, it is accredited by NAC with the highest grade of A plus, and holding 160th out of 1,071 applied institutions. This is a NIRF ranking, and the college has been started in the year 1994. Since then, it is running successfully, and we are having 10 UG departments and around 6 PG departments. About our department, since 1994 we are running this department successfully. It is NBA accredited. The main advantage of our department is around 50% of our faculty members holding doctorate degrees, and we are well equipped with modern laboratories. About the speaker is our alumni. It is an elite alumni. Presently, is doing his research in robotics and autonomous systems, Arizona State University, USA. He has published many papers in international journals and conferences during his UG studies also. UG studies and now presently he has conveyed many papers, and he has received many scholarship awards including ISA and IEEE. Now I hand over the session to Mr. S.M. Jayasurya. I think this session will be very useful with respect to the research point of view. I hope this will be a very enjoying session. Now I hand over the session to Mr. S.M. Jayasurya. Thank you.
Very good morning to everyone. Hi, I'm Jayasurya. I'm currently doing my master's at Arizona State University, and I'm doing my master's in robotics and autonomous systems with a specialization in artificial intelligence. And thank you, Department of Instrumentation and Control from St. Joseph College of Engineering for organizing this webinar. And I feel proud, and I take this opportunity to uh, convey whatever I have learned so far to many students like you and people, so that you can benefit from it. As I believe in pro-teach learning, one learns more by teaching others. So let's get started with the presentation. So the topic for today's presentation is reinforcement learning, and let's get started. So before that, let me talk about my journey so far. So I completed my undergrad from previous year, in the year of 2019, from St. Joseph College of Engineering, a college affiliated to Anna University. And I did my bachelor's of engineering in instrumentation and control, and I am very proud to say that I was a Anna University gold medalist for our department, for all the affiliated colleges in throughout Tamil Nadu, and it was a very proud moment. And apart from that, after once I finished my undergrad, I joined Arizona State University for my master's in robotics and autonomous systems, where I specialize especially in artificial intelligence. And like, my transition from bachelor's to master's has been I would say like St. Joseph College of Engineering played a huge role in it, and especially my mentors during my undergrad, Dr. R. Koteshwaran and Dr. R. Selvakumar sir, who had constantly motivated me and guided me throughout my career. And yeah, so and I had got ample of opportunities when studying at St. Joseph College of Engineering through hackathons, competitions, etc. I had published six papers in international conferences and journals during my undergrad, and all the credits goes to my mentors. And yeah, so like that's my past. So what do I do now? What do I do here at Arizona State University? So I work as a graduate researcher at Arizona Biomedical Collaborator, which is a national research facility here at Arizona, which is a state in United States, where I work under Dr. Edward Ofori at the Pathomechanics and Neuroimaging Lab, where our research is mainly focused upon early detection of Alzheimer's and Parkinson's related disorders. So we conduct a series of MRI, EEG, and EEG based protocols where we we get regular patients who are healthy as well as diseased, and we conduct a series of physical as well as cognitive tests to test their ability while monitoring their electroencephalogram and electrocardiogram. At the same time, we also take the MRI, that is the magnetic resonance imaging. So what role do I specifically play here? So we have our like since our research is focused upon detection of Alzheimer's disease at early stage, so we have a specific region of study in the brain, that is the substantia nigra. So I developed deep learning models using TensorFlow and RCNN for the volumetric analysis of dopamine, which is a substance present specifically at the substantia nigra, whose concentration goes on decreasing as the stages of Parkinson's disease, Alzheimer's disease increases. So apart from that, I also do AI-based cybersecurity research, where I'm part of a group called Secured Networking and Computing here at Arizona State University, where our team is guided by Dr. Dijiang Huang, where we mainly focus upon improving the security system, a security system by applying AI principles. And some of the projects that we are currently working upon includes machine learning based detection of advanced persistent threats. In this project, we mainly try to focus upon mimicking the activities of an hacker to improve our system. And in AI based autonomous penetrating testing, we improve the security level, where we apply AI principles like partially observable Markov decision process. And here we also try to generate synthesized data that is of high quality in order to create our own data set for the testing. Now, I guess everyone should be familiar with some of the machine learning concepts like supervised learning, unsupervised learning, etc. So for all of these, you need data. And so when you try to improve your security of a system, you need quality data so that your system that you form is highly robust. So here we apply GAN based systems to generate our own quality data. And we also do facial recognition and anomalization in video surveillance data for improvement of security. Apart from this, upon my personal interest, I do my reinforcement learning research under Dr. Yu Zhang, and that is what has motivated me to give this give this webinar on. So some of the projects that I have worked upon, as you could see, are developing a deep Q network based Pacman agent, and then value iteration network based human follower, and then lifelong planning based algorithm application in the Pacman domain. I guess these should be a bit of technical jargon by now, but at the end of the webinar, I think I guess like you should be able to understand what these projects are, as I'll be giving a demonstration for these projects. So let's get started now. So the agenda for today includes well, first we'll be discussing about different classes of learning, and then we'll like see what are the key concepts in reinforcement learning, and how significant is a queue function, and what are the different types of deep reinforcement learning algorithms, and then we'll compare one of the most hottest research topics that goes on, the imitation learning against the reinforcement learning, and we'll also see some cool projects and real life applications of reinforcement learning. So let's get started. So when we say like different classes of learning, let's get started with the help of supervised learning. So here the data that is your input is a labeled data, in the sense what like you have like for example here you are trying to classify a set of fruits. So like your input data that you'll be getting would be with the label. For example, an apple will have a label of apple, a banana with a with an label of banana. So with these you train your neural network or your model first, and then when an unknown like a new data, a test data is given without a label, you try to predict it. So for example, when an image of banana is passed, you try to learn the function to map the data to its label, and you try to identify what it is. Now after that you have something called the unsupervised learning. Here you just have data, you don't have labels. So what your model tries to do is like it tries to learn the underlying structure between the given images. So it's basically clustering. So a set of given images, you try to cluster those images that have similar attributes. So like for example here in the case where something that is long and yellow in color, you can classify them like into a like you can cluster them into a single group. So and you can, that is unsupervised learning. Then you have reinforcement learning, where all the data is a set of state and action pairs. State and action pair here means state is the current situation of the system, and actions are supposed to be like uh, like uh, like for a given state you can have multiple actions, and over the period of time what you do try to do is like you try to maximize the rewards that you try to obtain. Here your reward is acting as a feedback network. I guess like reinforcement learning would like, I know it should be a bit hard to understand now, but in the further slides you will be able to understand it. So one of the key understanding or the output from reinforcement learning for an banana example should be something like this. Eating this, for example, in a given state, you were given a banana, that was your state, and the actions could be something like this: throw it away, store it, or eat it. And over the period of time, when you have multiple episodes, you saw that eating the banana had a reward that was like it was helping you to keep yourself alive as well as healthy. Assume you just had banana to eat, and this is what your understanding is. So you understand eating this because it will keep you alive and healthy. So uh, so today's focus is reinforcement learning. So like before going into the topic, why do we actually need reinforcement learning? So this was something that I was really curious about, or I could say like I came on the opposite way. I didn't know what reinforcement learning was, but I knew what intelligent machines were. So I came to know about intelligence machines throughout my childhood, where through movies you have seen robots performing awesome tasks, and you also have seen you have read so much news and seen so much development going around using autonomous vehicles, smart sensors, intelligent devices coming upon. And then the other reason was could be something like you want to help the mankind through your activity. So that could be something like robotics, medical robotics, developing robots for medicine. So these are some of the motivation factors that led me into the field of reinforcement learning. So now when we start with reinforcement learning, there are some few concepts or key terms that we need to understand. So let's first see what an agent is. An agent is an entity or the main part of the reinforcement learning. And in case in general life, we as humans are the agents, and you have something called environment. For example, if you're trying to use a food delivery bot to deliver the food to a specific location, here your agent becomes the bot that you're using. And the environment is the surrounding in which the agent acts. So uh, the the state of the agent is specified through various sensors it is accumulated with. And and you have something called actions. So for example, when a robot, for example the food delivery bot, your bot is trying to deliver a food to a location, and it has like it can have both continuous action space as well as a discrete action space. A discrete action space would be something like move left, move right, move up, move down. And a continuous action state would be something like move left with the velocity of zero point 0.5 meters per second. So here, when you say a discrete and a continuous action space, it is quite obvious that your discrete action space is gonna be smaller, which in turn would be easier for you to select the action. At the same time, a continuous action space is gonna be really tedious. So, based upon the action that an agent chooses, it will get a reward. So now the rewards, which will in turn change the state of the agent. So now the reward can be of two types. One is like instantaneous reward, and the other one could be like where you earn the reward at the very end. For example, assume a team is playing a football. So here your ultimate aim of the agent, you assume like you have a multi-agent system that is like 11 players in a team or 11 different agents. The overall collaborative goal of the agent is to win the match. So it doesn't matter how early the team scores, at the end it will get the reward no matter how many goals it scores. So that is called like getting a reward at the very end. And like instantaneous reward could be something like in case of a food delivery bot, the faster the bot delivers the food, the higher reward it will get. The reward could be something like money, or something that defines how good the agent is actually performing. So here the reward basically acts as a feedback for the agent to get to know about itself, to see how it's actually performing. Now the when you see the total reward, the total reward is nothing but from a given instant t, the total accumulated reward over the period of n discrete time sequence. The summation of these entire rewards is the total reward. And you have and the other thing that is known as the discounted total reward. Now the discounted total reward actually helps to improve the performance of an agent. So like here, like as you could see, it's similar to the total reward, but you have something called here, like you have the weighted sum of rewards, where your weight is nothing but the gamma, which is the discount factor, to the power, like the iteration, to the power of iteration. When so basically what it tries to do is that the sooner it gets the reward, the higher would be the total reward sum. Since like your gamma factor is between 0 and 1, like as the the value, like as the power value goes on increasing, it's like gamma power would like ultimately that value becomes smaller. So here like your agent would try to get as many rewards as possible at the initial stages itself. So now we saw what a reward function is, and like this is defined by the r of t and the gamma. So now we need to discuss something called the q function. So like as we discussed here, the q function is something that takes a given state and a given action, and it gives a return of estimated like the maximum expected reward for a given state in a given action. For example, as we said, for example, if your bot is trying to move from location A to location B, and the location B is to the left of location A. Now your bot has like total of 5 actions available: move up, move down, move right, move left, and stay at the position. So as we could see, these are all the different actions available, and by choosing now when you choose the action right, since your if the point B is located to the right of it, so you'll be getting a larger q value. So in general you could say that the q function, like larger the q function, the higher the reward, the better the action that you have taken is. Now we know like the q function helps us to determine the best action. Now when we choose the when we choose the action based upon the q function for that has the maximum value, would give you the ideal policy. So the ideal policy is something that in turn actually tries to increase the total reward. Now as you could see, like when you have a given set of q function, now like the most tedious thing in a reinforcement learning is coming up with the q function. So here when in general, since you have both states and actions, like the combination of these two can since the combination of these two can map up for a q value, and it could be quadratic, or it could be of power 100 too. The relationship between each and every action corresponding for a given state that maps the q function can be really tedious. So that is something that we need to look upon. And when we now since we are done with defining all the main topics, now when we go into the deep reinforcement learning, the deep reinforcement learning is nothing but introducing a neural network for training the reinforcement learning. Now it is of two types: one is the policy learning and the other one is the value learning. Here in the value learning, what you try to do is like you find the q value, and then based upon the q value you apply all the different actions and you choose that action which gives the largest q value. So here you have two different actions that you need to perform: finding the q value and finding the best policy. And then the other one is called the policy learning, where you try to find the best policy without actually calculating the q value, q function. So it's which in turn like reduces by one step, and policy learning would be a bit more faster. So now first let's see how the value learning works. Now I guess everyone in the childhood would have played this game at least for once, the breakout game, where simply like you have a tile that is present at the bottom which can move left and right or stay in the place, and you also have a ball that is trying to come down, and once it hits the plate it goes up. So the major major objective of this game is to break all the cubes that are present above of different layers. At the same time you have to maximize the score. the maximization, at the same time you also have to balance out the ball such a way that it doesn't fall down. So here, like, how can we define a queue function? It is of really tedious task, because when you try to move to the left or right, how do you actually control the plate? You can actually give the entire force that will in turn move it to the extreme left or extreme right, or you simply don't apply any force. As a result, the plate would stay at its place. Now, so how do we actually come up with the q values? So for this, let us consider two scenarios here, the A and the B. In the A scenario, the policy is highly conservative, where what it tries to do is that it tries to place the ball that is coming back at the center of the plate. So say, the major thing with this thing is that it will never move to the left or right whenever it sees that the ball is properly aligning with the center. And you have the other, like in case of B, you try to hit the ball in a direction such a way that it hits the edge of the plate. So can you see the difference in how these two are going to act? Let's see in case of A. In case of A, as you could see that it's trying to hit the ball at the center. So what happens is that it will take huge amount of time to finish everything. Now let's see in the case of B. Now, in the case of B, as you could see, like with a single hit, it was able to cover almost like more number of blocks at the top when compared to that of action, like the scenario A, the policy A. So this is fine. We came to know about how this actually works. So how do we actually implement the deep queue network for this? So deep queue network is nothing but you implement your deep neural network to form the queue function. Since like forming of queue function is really tedious, what you do is your input, like you can actually train your deep queue network in two different ways. In the first way, like your input is gonna be the state along with the action, where the state is nothing but the image of the current state, where it signifies the position of the ball, and also the position of the plate, and it also indicates the number of blocks that is present. And you also pass the input for action A, and your deep neural network, nothing but it is made up of convolution layers and fully connected layers. And your expected output is nothing but the policy value, the q value for the given state and the action that we chose. Now, for example, if your action space has, in this case, you have left, right, and staying at the same position. So let's consider this discrete action space. So for a deep, in order to find the best q value, we need to run this network three times. What will be in case of n when your action space is of length n? So here you have to run your entire neural network n times, and then for each every action pair, every state and action pair, you will determine the q value, and based upon the q value, you will select the best q value to choose the action or to choose the policy. But the other the other method could be something like this, where you just pass the state of the input, state as the input, and your deep queue network in turn, like it selects each and every action from its action space, and in a single go it calculates all the q values for all the possible state and action pairs. And from the given state and action pair, you can choose the best best action that is in turn gonna be your policy. So, why do we need to choose the best state and action pair? Like, since if we choose a best state and action pair, you'll in turn get a larger Q value, which in turn increase your total reward that you will get. Total reward is nothing but the total score that you will be getting at the very end. Now you have something called the total target. The target is nothing but the summation of the reward for choosing that action, along with the product of the discount factor and the q value that we chose, which in turn and you have something called the predicted value, which you will be getting from the first neural network, case A. And you form the loss function by taking the root mean square of this, root mean square of this, and using this loss function you try to update the weights of your neural network, so that your so that your neural network is able to determine the best q value. So now, like, this is the overall functioning of the deep Q network. As you could see, like, you get the initial state S, and you pass it to your deep neural network. Now assume you have three different actions, A1, A2, and A3, that is left, right, and stay at the same position. And assume the neural network gives your output Q values as 23 and 0. So your policy is something that is going to choose the best action, and the best action in turn depends upon the highest q value. So from this you will select the action a1, which is moving to the left. As you could see in the image, that the ball is towards the left. And it'll like you, in order to like balance out the ball with your plate, you have to move left. And this will in turn, once you choose the action a1, now, after choosing the action A1, your state will currently change, which is passed as a feedback to the state S, and you will update and get the new state as S dash. Now, this is fine. So let's see the internal structure. So this is one of the deep neural network structure that was developed by DeepMind, where you have a series of convolutional neural networks, which takes in the inputs as the images, and input images are in turn like basically what you try to do is like you try like you apply convolutional neural networks to determine the features that could be something like edge detections. And like using that you determine you apply convolutional neural networks to determine the features. Once you are done with your convolutional neural network, you apply fully connected layers, and like you update the weights of your fully connected layers based upon the feedback, that is the back propagation that you apply. And you choose the choose the actions, that is like left, right. This in turn is for an different game. As you could see, like at the output you have all the different actions that are possible, and your neural network will select a particular action based upon its current input state. Now, these were some of the results that were obtained. As you could see, this compares the agent's average score and the average predicted action value. And like both of these values are pretty similar, but the scales are different for A and B. That's why the curves might look different. But if you observe closely for each and every epoch, once you train it for 200 epochs that is being given, the values are pretty close, which indicates that your DeepQ network is able to perform very well, and it is able to match the output, the actual output a human player playing it would obtain. Now, this was not just for that breakout game. Actually, the Google's DeepMind, they applied deep neural network, and these were the output, like the results that they were able to give. And here you could see the score that the DeepQ network was obtaining in blue color, and the gray color indicates the score that a human who is a master, who plays very well in that particular game's output. And you could see that you can uh, you can attain superhuman level of performance using DQ network for most of the games. And which in turn indicates that DQN performs very well in case of a discrete action space. So, like, since we are talking about the advantages and the performance, that is way too beneficial for a DQN. Now let's see what are the drawbacks of Q learning. Until now we saw like the DQN performs very well when your action is discrete and your action space is very small, and the policy is something that is determined deterministically. Deterministically means nothing but at each and every, no matter how many times you run your DeepQ network, your output is not gonna change. Since you're gonna choose a particular action from your action space. But what about when you have a continuous action space, where in turn as a human, when we play a breakout game, we actually not just control, like we just not just keep in mind the direction in which we have to move the plate, but also we control the velocity with which we slide the plate. So when we take in consideration of both velocity as well as the direction, then your space action space becomes continuous, and stochastic process is nothing but you chose randomly from your action space. So in turn, like your DeepQ network will fail in both of these cases, and let's see how we can actually improve it. Now we saw like the value learning. Now let's see the policy learning, which will actually help you to get the drawbacks from, like you overcome the drawbacks that we're obtaining from the Q learning. Now, like just for a recap, this is what our DeepQ network is doing. You have the input state, and then you have your deep neural network, which will in turn like give you the outputs of the different Q values for different actions that we choose, and we try to choose the policy based upon the largest Q value, the argmax of all the Q values that is possible, and our policy becomes that action which has the largest Q value. Now, let's see how a policy gradient method will work. Here, what you actually try to do is like when a for a given state S, your deep neural network tries to give the probability of each for a given state, like it gives the probability of each and every action such a way that it gives the highest Q value. Here we are not trying to actually calculate the Q value, we are just trying to find which action will be giving the largest Q value based upon the probability. As you could see here, like the action, when you perform an action A1, your probability of getting the largest Q value for like for a given state S, when performed action A1 is 0.9. When you perform an action A2, that is J, you have a probability of 0.1. And then like when you take a right, when you the action that is A3, that is right, you have a probability of 0. I guess like that should actually be intuitive here, since your ball is going towards the left direction, and in turn like staying at the same position, you have the probability that you might actually hit the ball at the very edge of your plate. But if you try to move towards the right side, then it's you're actually moving on the opposite side of the ball that is actually coming. So like you will be performing poorer, so you actually should not be choosing that action. Hence your probability like of obtaining a good Q value, like the largest Q value, is 0. But in turn, if you try to move towards the left, you have a higher chance of hitting the ball in the center of the plate, hence the probability is high. Now, since we like see as a uniform distribution here, the summation of probabilities should be equivalent to 1, and based upon this you choose your policy, that is the one with the largest probability distribution. Now let's consider a Gaussian distribution or a continuous distribution for a discrete set of actions where you have the left, right, or staying in the same position. Your distribution would something will look something like this, where it is only at the specific discrete points. But for a continuous action space, what you obtain is the entire area over which you're like you try to determine each for each and every point on the both left as well as the right space with with the speed you have been moving. So when you like faster you move it to the left and faster you move to the right, the variation of your probability distribution can be seen here. Since this is a Gaussian distribution, and we know that we can since a Gaussian distribution has a direct relationship for its mean and variance, that is nothing but the center of your spreading is gonna be at your mean, and the variance is gonna indicate how much your probability space is gonna spread. Now, as you could see in this curve that is being plotted below, the -1 is the centroid and the center point, and you could see that that is your mean, and you obtain the largest value at your mean, and then your variance is 0.5, which indicates the spreading on both the sides. And based upon this, when you take the when you calculate the area below the curve, it should be 1, and you try to obtain the point where your probability at the is at the highest, and you try to choose that action space, that is nothing but you directly actually come up with the value, that is like for example here minus 0.8 meter per second. That is the speed by which you have to move towards the left in order to like the balance out the ball at the plate. Now we saw like how these two ideas, I guess like it should have been like a bit tedious since it had more calculations. But I guess like when we try to understand it using a case study, that is in turn you should be able to understand it more clearly. So let's see the case of a self-driving car. So as we initially described these things, and you have an agent which acts in the environment by taking some action from its action space, which in turn changes its new state, that goes from S to S dash, and then for choosing the action you get a reward that is nothing but R. So let's that is what is being defined here. For in case of a self-driving car, your agent is nothing but the self-driving car, and the environment is nothing but the road or the path in which the your self-driving car is moving along with the pedestrians and other vehicles. It's simply the surroundings of the agent, and the state is nothing is the position, like the state of the agent can be obtained using like the various sensors usually present in the self-driving car. So when it comes to self-driving cars, you have actually like different teams working with the self-driving cars. You have something called the perception team, you have the mapping and localization team, you have the controls team, and I'll explain you how each and every team works. So in case of a perception team, so the major goal of a perception team is to identify all the objects, and in for that like you use something called the cameras and the lidar. Camera like for complete or a good performance of your self-driving car, you need the 360-degree view of your surroundings, so that you can map each and everything properly, and you can determine how far or how close an object is, how is something is a new vehicle interfering with that of our lane, and etc. So you use cameras and lidar. Lidar is nothing but laser, which is light detection and ranging, where you the lidar works in such a way that it it expels out the lasers in different directions, and once the laser hits a new object, it in turn develops the dense map. It's nothing but it determines how far a new object that was being hit by the laser is, and with that you map your surrounding. And planning and localization team is helps uses something called the SLAM, that is simultaneous localization and mapping, which in turn uses lidars to find out your surroundings, and to come up with the proper path. You obviously, when you travel in a car or in a vehicle and you are running short of time, your major goal would be to reaching the destination as fast as possible. But your major goal would also be traveling safely. So here the planning and localization team comes up with the proper route, and the controls team in turn works such a way that your when you see your actions, that is nothing but acceleration, braking, and the steering control, which is in turn based upon your environment. So you have the traffic light signals, and you have your surrounding vehicles, and you have the pedestrians, and there could be like sudden cases that you there might be a vehicle that is coming very fast in your blind sight, and you need to react very quickly. So based upon the perception themes, where it determines the different objects, and that is being passed as the feedback. Based upon that feedback, your control team controls the acceleration, braking, and steering control. And here your reward function is nothing but safe commuting, and reaching the destination. So like how does this training actually happen? So you first initialize your agent. Nothing It's nothing but you start your agent for a given given from a given location, uh, and then you run a policy till termination. So as we just discussed, what a policy is nothing but choosing the best action for a given state, and an optimal policy is nothing but choosing the best action for a given state. So we never know, like at the very beginning, that if your agent is going to choose the best action or not. So what you try to do is, like, you start your agent and you allow the agent to run until termination. The termination could happen in two ways, where it might collide, or it might actually reach the destination, where that is like it travels in the path without colliding to the left or right, and it actually goes in the planned path. So once you find out that your policy got terminated, what you try to do is, like, you try to find all those states and action pairs which were in turn actually having giving you a better results. Then, for example, the initial stage S0, S1, where actually taking your autonomous vehicle in the proper path. So what you try to do is, like, you try to increase the reward of those state those actions, while the S2, S3, like S2, S3, and S4 and S5, which were actually causing you to collide to the right, you'll try to reduce the rewards for those functions. Now, in order to control these rewards, since we are using the policy gradient method here, what you try to do is, like, you decrease the probability of actions that result in a lower reward, and you try to increase the probability of actions that result in a higher reward. Now you train this until and unless you just go on increasing, but you just go on increasing and decreasing your weights of your neural network, and then at some point of time you should be able to obtain the proper combination of weights, such a way that your deep neural network gives the optimal q values, and you choose the optimal action to get the optimal policy. So that's how you train an autonomous vehicle in general. Now, uh, like like as we just discussed, like, you increase the probability of actions that result in a higher reward, and you decrease the probability of actions that resulted in a lower reward. So how do we do that exactly? So in order to do that, here we have the loss function in the form of the product of log likelihood and the reward. The log likelihood is nothing but it gives an estimate of how likely are you to choose the given action at for a given state s of t. And reward RT is nothing but what is the total reward that you obtained for choosing the particular action 80. So based upon that, now for example, if your action is like, if assume like when you choose an action, the action was actually the optimal action, then your probability distribution, the P of 80 given ST, is going to be very high, which in turn will make the reward RT that is being collected at the end will also be very high. So when you have two, like the probability, and when you take the log of your probability and the summation, and when you multiply it with a negative symbol, your loss becomes very small, as you multiply two big values, and taking a negative of a two big value product of two big values is gonna give you a very negative value that is very small in turn. So now based upon this log value, what you do is like you train you adjust the weights of your neural network by taking the gradient of this loss, and which in turn is based upon increase, it could be based upon decreasing your weight by taking the gradient of the loss that we are obtaining. uh, Gradient is nothing but obtaining the partial differentiation for each and every action for the particular state, and adjusting its weight based upon the reward that it obtained. Higher the reward, the smaller the change would be, and the higher the probability of that action being selected as the optimal action. So this is how you train your neural network to obtain the best combination of weights, which will in turn cause your neural network and your autonomous vehicle to perform better. Now, this is fine. So, like we just discussed, like we run a policy until termination. So, is it actually safe to run a policy until termination in a real life scenario where these are like some of the results that I saw. So the accident of the Uber's autonomous vehicle and the Waymo's autonomous vehicle both happened in the previous year at Arizona. And fortunately, I didn't. Unfortunately, or fortunately, both I didn't see them, but I came to know about them. So, like terminating a policy, running a policy until termination, can have a huge wealth of loss, which like since each and every company spends so much amount of value for each and every sensors, till for the cameras for a vehicle, it is not that easy to like directly deploy a vehicle in the roads and test it until like it hits someone. What if it hits a pedestrian, which in turn will cause a life? So these are really uh, harmful, and this is not a good way to actually train your model. So so how do then these companies actually train their models? So what they actually do is something called the making of simulators. As you could see, like this is an Nvidia simulator. On the right you have the actual live feed of a camera fitted to a car, where it's detecting the different vehicles that is along the path, and it's tracking them whether it's colliding with the same path or not. And on the sorry, on the right you have the simulated version of it. You could see that it maps each and every object pretty closely, and as you could see here, it's mapping the acceleration too. And when it sees that the object is coming very close to that of our vehicle, it tries to apply the brake. So this is how you develop a simulators, and developing a simulator is also a bit tedious task, since you need patience. But one good thing with simulation is that you have so many online games or offline games like NFS, etc., and then like Grand Theft Autos and stuff, where you can actually get the animated data, and using that data you can actually train your neural network, and which will in turn train your model. But one thing that we need to consider is that we need to map the real world, map the simulator as close as possible to the real world. Now, these are some of the different simulators that are being used by some of the autonomous vehicle companies. Here, the Zoox and Torque are one of the startup companies for autonomous vehicles here at the USA, which I have been closely following, and they are actually doing in turn a very good job upon how closely they are developing the simulators to the real world. So the mapping plays a very big role, and it's like some of these tools are open sourced, so you can actually see them, but the others are not open source, so you can't use them actually. So till now we saw like how the autonomous vehicle is being trained and etc. So now comes something called the imitation learning. So I guess like everyone would have heard at least once what an imitation learning is. Just see this image here. Your robot is actually trying to mimic what your human is doing. That is exactly what an imitation learning is trying to do. It tries to mimic the human behavior for a given task, and an agent is trained to perform a task from demonstrations. It is not just like with a single demonstration your agent would be able to mimic it. You need to give hundreds of demonstrations for your agent to understand what you are exactly doing. And what are the other advantage? You need minimal expertise for the knowledge of the task that you are performing. In simple, even if you don't know how to perform a backflip, you have thousands of videos that are available online. You can just download them and make them as a data set, and you can use them to train your robot. Well, it also actually helps to eliminate the programming. The major part, the major hard thing for a neural network is designing the reward function, and which we saw that's because like coming up with the proper q value is always difficult. At the same time, choosing like giving the reward for each and every action is also difficult. So it's like the imitation learning eliminates the difficulty with the reward, and that is a major advantage when you compare the reinforcement learning. So what are some of the different types of imitation learnings that we have seen? So this is something called the time contrastive networks, self-supervised learning from multiple views of observation. So what it's trying to do is like you have like for example here in this task an agent is trying to perform sit-ups, and you have different cameras where you try to map like where you try to film the same task from different angles, and you form this as your data set. Now when you pass it to your simulator or your simulator, what it tries to do is that it tries to find the attributes of the agent in turn, which is the human that is performing the task. Those attributes which change which do change on different views but does not change over the period of time. So it tries to see what are those attributes, and it collects those attributes and it trains your robot based upon those attributes. That is what the time contrastive network does. Then you have something the same thing like with an example where here you could see an agent like a human is trying to pour the the coke or the pepsi or the cool drink soft drink into a glass, and the same thing is again being mimicked by a robotic arm. So this training which will in turn take would have taken actually like huge amount of training data set. It would have taken large time to train your robot to perform this task, and you should have actually trained your agent with large amount of data set. Now you have something called unsupervised perceptual reward. So this is nothing but like we discussed, getting a reward function for a action being performed is really tedious. Here, this model tries to evaluate that particular reward function or the reward value for the action being performed for the given frame. So it's not gonna give you a function for a reward, but it will in turn estimate the reward for the action that it is doing for the given action. So like as we said, like both imitation learning as well as the reinforcement learnings have their own advantage and perks. And what if we try to combine these two? So this was done by the DeepMind's DeepQ learning for demonstration, which appeared at the AAI AAAI 2018. And what it basically tries to do is that when you have some amount of data that you had obtained by demonstration from a person, you try to use this data to train your reinforcement learning, which will in turn try to like come up with the proper optimal value of your cues and your rewards as soon as possible. So vanilla means nothing but the it's the general gradient descent reinforcement learning training that you do to increase your adjust your weights to obtain the proper parameter values. Now the simple goal of your the DQFT is to use the data to pre-train an agent so that it can perform the reinforcement learning right away and it can be effective. So it is in two phases. In phase one, the agent does not do anything, but in turn it tries to perform the gradient descent from the data that is already available, and it tries to minimize the loss function. But and in the phase two, what it actually tries to do is that now the agent tries to explore the environment by itself and it collects its own new data. But what it tries to do is like it does not lose the previous data that was already given by some trainer. So it keeps both of them together, and keeping them both of them together, what it does is that it splits the both of these data into mini batches and trains them alternatively to adjust its weight so that it can perform optimally. So in simple, your DQFT uses a greedy policy with a smaller epsilon value, which will in turn help you like to have lower number of exploration. That is nothing but for example, for a given state, if your action space is continuous or like discrete. In case of a discrete, assume you have n discrete actions that are available. You can choose either like any one of them to arrange or like attain your optimal policy. But what your DQFT tries to do is that it tries to minimize the number of actions that it has to perform to find that best action. So that is something it does by using the mini batch technique. So now let's see a project that I had recently done. Uh, the overview of this project is nothing but you have a bot that is going to move across your environment, and your environment consists of two types of banana. One is going to be yellow in color and the other one is going to be in blue in color. Your major objective is to train your agent such a way that it tries to pick as many yellow bananas as possible, and at the same time it should avoid picking up the blue bananas. So when you actually deploy an untrained agent, which in turn like performs very stochastically, it chooses actions very randomly and it performs very poorly. As you could see, it's not, even though it's very close to the uh, yellow banana, it's not trying to collect them. And let's see like what happens with the partially trained agent. So here with a partially trained agent, it now the agent is able to collect some of the yellow bananas, but the major problem occurs that it gets stuck at the local minima whenever it sees a blue banana. So it's not able to go across the blue bananas. And it had an average score of 9. That is like it was able to pick up 9 bananas over the given period of time, but I think it was mapped along with the time sequence. So it not only did, like, it's indicating the number of bananas collected, it also detects the efficiency, like over the given period of time, how many it was able to collected. So it's a discounted reward value that is being shown. And then, like, when you have a fully trained agent, it performs really quickly and really well. It tries to collect as many yellow bananas as possible, and in a very small amount of time. At the same time, it is able to avoid the blue bananas. So yeah, so let's this was one of the projects. Now let's discuss one of the other projects that I have recently worked upon. That is nothing but developing a deep Q network based Pacman model. As we just studied about the, as we just went through about the deep Q networks, how they work, and I tried to implement the deep Q network in a Pacman world. I guess like everyone should have come across this game at least once in their lifetime until now. The game is nothing but it's pretty simple. You have an agent called Pac-Man, which is a yellow, which is in yellow in color. It lives in a world which is filled with food pallets. Food pallets are nothing but the white dots, and you have something called the power pallets, which is the same white dot, which is slightly bigger in shape. And you also have different other agents that are shown in blue and yellow in color. These are nothing but the ghost. The major, like, it's a multi-agent environment where you not only have to look upon your agent, but you have to also consider the other agents that are present. So you have to collect all the food pallets at the same time. You should not get like caught by a ghost. So, like, when like initially after training for around 2,500 episodes are nothing but the like episodes are nothing but different scenarios, and which are being automatically generated here. And when, like, initially when it was partially trained, it had a win percentage of 35% when trained over 2,500 episodes. And then when I had trained it over 10,000 episodes, the win ratio was very high. That was around 92%. So, like, in one of the other project that I would like to demonstrate is the human follower bot. Here, you're trying to, like, follow a human model with a turtle bot, and the turtle bot's objective is to follow the human wherever he goes. The human is going to, like, the human has been trained or programmed explicitly to go to specific well defined goal locations where which are not known to the turtle bot. So here you use OpenCV, and this is without any reinforcement learning being applied. So, like, you have the OpenCV, which determines the bounding box, and based upon the bounding box, it has a stereo camera. With the help of stereo camera, you estimate the depth of the centroid, and that in turn calculates how far you are from uh, from the human, and based upon that, you control your steerings. Now, here you have like one more example where you have trained your human model with the value iteration network, and where you're just simply trying to follow it, but without applying any OpenCV here. In turn, like, you're not trying to find the bounding boxes. Now, which can be seen here, when you deploy an untrained human bot, the bot gets stuck at a point and it's not following the human, but the human is still moving around, as you could see. And when you finish a fully trained model, here you could see without the bounding box, the turtle bot is able to follow the human wherever it goes with an average accuracy of 83%. So these were, I guess, like, you would have liked these projects. So these were some of the references that I had used, and like, I would like to thank St. Joseph College of Engineering and International Society of Automation for organizing this webinar, and thank you. So I guess like now it's time for Q&A. You can drop in your questions in the chat box, which I'll be able to answer them. So I could see a question from Selvi Muthu Krishnan. For imitation learning, is training will be less compared to reinforcement learning? No. Actually, like you need to train your model more. In case of like imitation learning, that's because you are not controlling your weights directly. It's gonna you need to train it more actually. And then there's a question from Sindhil Kumar. What is the difference between maximum likelihood and the log likelihood? So the maximum likelihood is nothing but it gives the maximum, like it gives the max rate at which you might choose an action, whereas the log likelihood will give a logarithmic value for a continuous set of action pairs. So when you have a discrete set of action pair, you might go for a maximum likelihood where you'll choose only the particular value of q that has the highest value, and you'll choose that particular action. But in case of a log likelihood, you will go through all the possibilities and choose one action. Are there any questions? So there is a question from Rahul, which is, can you explain about combinations of reinforcement learning and imitation learning in real life scenarios apart from projects? So yeah, so like I guess like you would have come across something called industrial robotics, where you have a series of robotic arms that are being deployed in industry, and there could be something called where you're trying to identify what a particular object is, and you try to place that particular object in its location. So here, for example, it might be something like a classification problem. For example, if you're like your rail bed is carrying some different objects like fruits and vegetables, and your robotic arms role is to separate, like pick the like fruit and drop it in the fruit basket and vegetable in the vegetable basket. So here you can do the a combination of like imitation learning with the reinforcement learning. So with the help of imitation learning, you will be teaching your bot to how to pick an object from the rail, and with your reinforcement learning, you'll be telling how to, like, which object do we need to pick. So how do we distinguish a vegetable from a fruit? That will be done by your reinforcement learning part, and your imitation learning part will do how to pick an object.
Jaysurya,
Yes, sir.
you have a question. Whether agent is an independent entity from GNR Prasad.
An agent is an individual, yes, an agent is an individual entity. He's gonna act upon its own, and whose states are being determined by the sensors. And you are trying simply in turn, it is gonna choose some action from its action space, and you are trying to control which action you need to choose upon. It could be a single agent or as well as multi-agent. perspective. In case of a self-driving car, you can have multiple self-driving cars going around at the same time, so it's a multi-agent game. Whereas in place of the banana project that I showed you, it's a single agent. You just have your single bot and you try to pick the yellow bananas alone.
So we have one more question uh, from Rahul Bharadwaj. How lesser probability can lead to lower reward?
Okay, so when you have a less probability, that means you less probability means your log value is gonna be smaller. Smaller at the same time, your reward is also gonna be small. So for a smaller value, for example, if your log probability is very small and your reward is very small, you take value of its log, it's gonna be a negative number, and you had a negative symbol before your log likelihood. So the combination, when you multiply two negative quantities, it becomes positive. That shows that your loss is positive. That means you have a higher loss. But whereas in case of a larger probability, your loss value was negative. So that's how it's gonna work. The lower the probability, higher the loss value would be.
So we have one more question
Hmm.
regarding the same uh, question. Why we need to combine both the reinforcement learning and
I guess I just
the
answered it.
question?
So.
Okay, I answered that. Okay. And then we have one more question. What are the higher studies related to reinforcement learning?
So you can it's not higher studies. So like how to start off it. It's a very specific domain. So you can start off by doing your masters in a field of robotics or in a field of mechatronics, where you can skip the domain where you need to specialize on in some topics, like your if you're really interested upon working on imitation learning or reinforcement learning, you can keep your track only upon focusing upon your reinforcement learning or imitation learning, and do your thesis in it, and which in turn you may actually, like if you're like even more interested in it, you might continue the same track and do a PhD. So there's no specific program that takes your higher studies only for the reinforcement learning or imitation learning in master's level, but in PhD level you do have them. So I think there's one more question about like deep neural network. So, like simply speaking, when we spoke about the reinforcement learning, we know that the biggest challenge is coming up with the Q value. So, since when you have a continuous action space, you can have many combinations of state and action pair, and which will give you different Q values. So if you try to map it by hand or by a person, it will take huge amount of time. But in turn, what you do with a neural network is that you given the state, and you have your action space that is already defined. Your neural network will choose your actions from your action space, and your deep neural network is simply built by convolutional neural networks.
அவனோட இமெயிலும் லிங்க்டுன்னு ஏதாவது போட சொல்லுங்க. கொஸ்டின் நிறைய பேர் இருக்கு.
Convolutional neural networks, and Uh, I think yeah. So if you have like more like simply speaking, your deep neural network is made up of CNNs and fully connected layers. Your CNNs are like your since your input is an image that is showing your state. You try to find the different features from your state, and you pass it to your fully connected layers. And based upon them, you choose your actions from at the end you have to choose an action, right, for a given, like based upon the Q value that you are obtaining, you have to choose an action. So you choose an action, which in turn will give you a reward. Based upon the reward, you back propagate that reward value to your neural network, and based upon that, you update your weights by up there, like applying gradient descent. So this is how you train your deep neural network. I guess I would have answered your question.
So Jayasurya,
Yes, sir.
thank you for the answering the questions. So now I hand over the session to Dr. Kotishwaran sir for the vote of thanks. And
Yes. I would like to thank the speaker of this session, Mr. S.M. Jayasurya, for a wonderful webinar. He explained from the basics, and it was a very nice session, and I hope you all enjoyed it. And at this juncture, I would like to thank our beloved chairman, Dr. B. Babu Manoharan, the managing director, Ms. Jessie Priya, director, Mr. Shashi Shekhar, our principal, Dr. Vaddi Sheshagiri Rao, our dean, ma'am, Dr. Parvada Vadani, ma'am, for giving this opportunity to conduct this webinar. And
Hello.
once again, I thank the participants for their passions, and we will meet in the another webinar. And I
Hello.
will end this session with the
Sure. I would like to
quote.
share my
Yes.
contact details
Yeah.
for. I think like lots of people are having their questions.
Okay.
Let me just share my contact details. I'll just share my screen for a couple of minutes so that
Okay.
they can
Okay.
note it down.
Yes. 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 It's fine.
Just a minute, sir.
Yes. Yes. Do.
Yeah, so these are my contact details. You can either contact me through WhatsApp if you want, and this is my number. Feel free to message any questions related to this webinar or like higher studies. Actually, I was planning to come talk a bit more about the master's program, uh, and like how to choose a college and all in USA as well as in different countries. But due to time constraint, I couldn't cover those topics. But if you have any questions, you can definitely WhatsApp me. And this is my WhatsApp number, and this is my email and LinkedIn. You can also like reach me out through email or LinkedIn. And once again, thank you everyone for attending this webinar and making it memorable.
Yes. Thank you, participants, for your passions, and we will meet you in another webinar. And we end this session with a quote: "Stay home, stay safe." Thank you. Thank you, Jashirya.
Thank you, sir.